Hello everyone. Today we shall discuss about thermodynamics, the rules of the energy game. From molecular chaos to the macroscopic machines that power civilization. You see here, thermodynamics is a macroscopic science dealing with bulk systems, disregarding the chaotic motion of individual molecules to focus on variables we can feel and measure: pressure, volume, and temperature, scope, the laws governing thermal energy, and the conversion of work into heat. You see here, this is a picture of, see, this is the pressure, this is the volume, and this is the state. This is the initial state, and this is the final state, and this is regarded as the work done. Now the core concept, heat versus work. Two distinct modes of altering the state of systems. You can see here the micro del W, that is work, that is work. You can see here that the work del W is equal to A changes to del Q, that is heat. The macro del Q changes to work del W, that is the micro work to heat and macro heat to work. Here work del W equal to del Q heat. Kinetic energy from friction transforms into thermal energy, increasing the system's temperature. Heat to work del W. Thermal energy from system expands is from steam expansion is converted into mechanical work driving the wheel. Historical insight. In 1978, Count Rumford disproved the calorific fluid theory by boiling water strictly through the friction of boring a cannon, providing heat and work are energy transfer modes. The zeroth law, defining the scoreboard. The law, two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. This transitive property defines the concept of temperature. The schematic arrangement of systems A, B, and C illustrates this principle. You see, this is the adiabatic wall, right? And this is the adiabatic wall. This is diathermic wall or conductor. This is heat. So therefore A and B are in between, there is a adiabatic wall, but between C and A there is a diathermic wall, and between C and B there is a diathermic wall. So what we get here, if TA is equal to TC and TB equal to TC, then TA is equal to TB, right? So here you get the zeroth law of thermodynamics, that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. This transitive property defines the concept of temperature. The schematic arrangement of systems A and B and C illustrates this principle. The player's energy in transit versus storage. Key distinction: a system processes internal energy. It does not possess heat or work. Heat and work are simply the methods used to change internal energy. Internal energy, or it is an state variable. Work, mechanical transfer, right? And this is the heat, that is energy in transit. Rule 1, the first law, conservation. Sign convention: plus Q, heat added to system, is regarded as plus del Q, plus del W, work done by system expansion, and del plus del U, increase in internal energy, that is converted, that is used as plus. So del Q equal to del U plus del W. The general principle of conservation of energy. Energy supplied to the system goes partly to increase internal energy and the rest to do work on the environment. A specific heat capacity, the energy budget. A specific heat, the energy cost to raise 1 kg of substance by 1 Kelvin. For ideal gases, Cp minus Cp equal to var. Expanding gases do work require extra budget of heat to raise temperature compared to gases at constant volume. You see, this is water, high specific heat, copper, low specific heat. So we give an example. Specific heat of water versus temperature. You see, this is the specific heat of water versus temperature. The graph will be like this. The snapshot, state variables. State variables describes equilibrium states that depend only on the current condition, not the history or of how the system arrived there. Pressure, intensive property. Temperature, intensive property. Volume, extensive property. Internal energy, extensive property. The equilibrium state ideal gas PV equal to mu, R and T, where P is the pressure, V is the volume, mu is the mole, R is the universal gas constant and T is the temperature. The quasi-static process. To apply the thermodynamic laws, we idealize a process as occurring infinitely slowly. At every stage, the system remains in perfect thermal and mechanical equilibrium with its surrounding. This is the real process, non-equilibrium. Quasi-static process, that is an equilibrium. This is here piston, state 1, V1, del Y, A1 millimeter, state 3, V3. So these are the quasi-static process. Move 1. Isothermal expansion. Constants. Temperature is fixed at the del U equal to 0 for ideal gases. All heat entering must immediately leave as work. So Q is equal to W or W equal to mu R T ln V2 by V1. This is isothermal process. PV equal to constant. So the work done will be in this. This is the graph of the work done in isothermal process. This is the heat reservoir temperature constant. So the work done will be found out by mu RT ln V2 by V1. Adiabatic expansion, constant isolated system, no heat exchange, del Q is equal to 0. Result, the system pays for work using its own internal energy, the gas cools down. So PV to the gamma equal to constant, that is the equation for adiabatic expansion. Here you see this is insulation, this is here cylinder, this is insulated system, Q is equal to 0. So the graph will be like this. This is the adiabatic process, the work done is this is the area of the work done, adiabatic process, that is PV to the gamma equal to constant. Moves 3 and 4, isoporic and isobaric process. Isoporic, volume locked, the pressure cooker effect, that is the volume locked. Isobaric, pressure locked, that is the piston moves freely to accommodate expansion. This is the isoporic process. Here the volume is constant, W equal to 0, all heat changes to internal energy. Isobaric constant, the pressure, that is this work done, P equal to W equal to P B2 minus P1. This is the work done for isobaric process. Rule 2, the second law, the reality check. Kelvin-Planck statement, no process is possible whose sole result is the absorption of heat and complete conversion into work. Efficiency eta is always less than 100%. For this statement, heat never flows spontaneously from cold to hot. Here the hot reservoir, this is the heat engine, this is the cold reservoir, QH, QC, and this is the work. Reversible versus irreversible process. This is the reversible, no friction. Irreversible, dissipation, real irreversible. Reversible, a quasi-static idealization where the system and surroundings can return to their original state. Irreversible, the reality of nature. Friction and turbulence dissipate energy as heat which cannot be spontaneously recovered. Engineering editorial, the theoretical ceiling, the Carnot engine. The most efficient engine possible between two temperatures, efficiency equal 1 minus T1 T sink by T source. Carnot theorem efficiency depends only on the temperatures of the source and sink not the working substance. So this is isothermal expansion, this is adiabatic expansion, this is isothermal compression, this is adiabatic compression. Summary: the laws of the game. The zeroth law defines the playing field temperature. The first law ensures the books are balanced conservation. The second law sets the winning condition efficiency limit. So here you see that the zeroth law is the defines temperature. That is, first law conserves energy, that is del Q equal to del U plus del W work, and limits efficiency less than 100%, that is the second law. Thank you everybody for watching this video.